All right, so we're going to go ahead and continue with discrete distributions. We've talked about binomial. We've kind of dug deep into binomial from a few different angles. And we're going to look at another distribution that encompasses a lot of different phenomena. Okay? And that's a good way to think about these distributions, that there's something in the natural world that we can observe that likely follows this kind of distribution. And that allows us to ask questions and answer questions and perform various kinds of analyses. And it also gives us a framework from which we can build other ideas of distributions. I think I mentioned this before where, okay, if we think of binomial as we've got some sample that we take, some Bernoulli trial, and let's say this is, probability of success of 0.5, and, this first trial we get, let's say we get a 0, right? We don't get success. If we want to take this idea of binomial and transform it into something kind of different, we could say, well, let's take the input from this and create a rule that means that success will be reduced by 0.1 or something like this. So maybe we do a minus 0.1, and then that means the probability of the second trial might be 0.4, right? And we're more likely to have a failure on that second trial. But let's say we have a success, and so now we're here. Well, now let's say that's going to increase the probability of success by 0.1, and so the next p would be 0.5 again. And let's say we get success, and then the next one would be 0.6, and so on. And let's say we get a failure there, and then it's 0.5 again. We can look at a procedural way to develop that distribution, right? Where each subsequent sample, each subsequent trial is dependent on the previous one in some way. We could do something like that, given that we have an understanding of the kind of general phenomenon of binomial, and we can sort of tweak it into something that isn't binomial anymore, but we can see that it's directly related. And at the end of this, we're going to count the number of successes. So we're still dealing with, the question of how many successes in n trials, but now we have dependency between the trials, right? We could do something like that. And I think that's an important way to think about distributions, in general. It's like we can say, this phenomenon perfectly follows a normal distribution, or perfectly follows a binomial distribution, or something like that. But we can also modify the analysis of the phenomenon to create its own distribution. And we can look at any number of, we can design these things, or we can observe them and try to model them locally, right? And at the end of this, we're trying to get out of this, I alluded to this before, you have this universe of functions, big F here, and you have some subset of functions that might give you, within some reasonable, or over some reasonable threshold, might give you a solution to answering questions about something you're observing, right? And out of these, you're going to select one function, and it doesn't mean that it's the best function, but this function will be able to answer some questions. It'll be able to answer, like what is the probability of, in that, previous thing that we looked at, what is the probability of getting 7 successes? What is the probability that we get 7 successes when we have this dependent sampling approach? Obviously that's a fairly simple phenomenon, right? We can model that, and we can create sort of a tree of possibilities. We can create the entire sample space and we don't even need to like search for a function. There is some underlying function that we can model, but things are weirder than that, right? Salmon swimming up a stream is incredibly complex, and we might be able to take a distribution and use that distribution to naively describe that phenomenon, right? We can put a whole bunch of constraints on it, but at the end of the day, we're probably not going to have the actual function itself. We're going to have some approximation that works for our purposes, and more likely we're going to build that function. We're going to use a machine learning approach to analyze some data that a machine learning algorithm will spit out a function that we can use, and that function will do as well as it does, right? Given the data that we have, how we've collected the data, given the appropriateness of that algorithm, any number of factors in there. So as we're learning these distributions, it's important to think about them as being in relation to some phenomenon. Yeah. And I think for me, the Poisson distribution is really great for this because it seems to tie into our natural world in some pretty great ways. So the Poisson distribution represents the number of events occurring in a given interval of time or space. And we'll kind of describe that in a little more detail in a second. There's this parameter lambda, and we're very often going to be trying to figure out what is our lambda. And lambda represents the typical or expected frequency in a given interval. What do we expect? What's the average that happens in a span of time? If we know the average that happens in a span of time, and we know that the events are independent, and each event is independent and identically distributed, then we can start applying the Poisson distribution to it, and we can answer a question like, if 5 taxis arrive in an hour, on average, in this span of or in this block in Brooklyn, let's say, I don't know, then what is the probability that 3 taxis will arrive there in 45 minutes? That's the kind of question we can answer, and it's kind of amazing that this distribution exists in that way, that we can answer those kinds of questions. There is an interesting clause here that I think about kind of a lot. 2 events cannot occur at the exact same instant. But if we think about time as being continuous, right, how is that even going to happen? I think that's an interesting constraint to throw on here. I've always wondered about it, and I need to dig into it more and understand that philosophically. But that said, let's start off with the probability mass function for Poisson. So the way we're going to think about Poisson is that we have, we'll root this into time, because I think it's helpful to think about this in terms of time. It's probably the easiest way to do this. Okay, we've got time. Time is this continuous thing. And we've got some bounds that we're considering. So let's say these bounds, let's say this is 5 minutes. In 5 minutes, on average, we expect to see, let's say, our lambda, in relation to 5 minutes, our lambda is going to be, let's say, 5 events, just to be simple here. Now, what are all the different ways that 5 events can occur in 5 minutes, right? Time is continuous. So those 5 events can occur in an infinite number of ways in a span of 5 minutes. They could all be clumped right here, right? They could all be there and evenly spaced from each other, or they could be, on this end but unevenly spaced from each other. There's any number of ways that this can happen, and that kind of leads to this. If I'm going to draw this from binomial, well, if we're thinking about binomial and we're thinking about on average 5 events in 5 minutes, well, maybe we would divide this into 1, 2, 3, 4. Oh my gosh, that's 6. Yeah, okay. Let's imagine these are all evenly spaced. These are all 1 minute intervals. And let's say in a 1 minute interval, we can have either the event happens as 1 or the event doesn't happen as 0, right? And we just look at that. So we could take a very naive approach here and say, all right, well, 5 events in 5 minutes, a minute is either going to have an event or not, right? And we could build that sample space. We could say 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, right? 0, 0, 0, 1, 0, and so on. And we can answer a question like, well, what's the probability of 3 events occurring? Well, that would be 3 successes and 5 trials. But we're dealing with a continuous value, so maybe or time as a continuous construct. So maybe what we would do is we would further subdivide this, right? And we would turn this into 10. And we're dealing with 30 seconds, right? We would have 10 trials, 10 Bernoulli trials, and but still we have 5 events, right? And the way that starts looking, right, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then if we were to build the sample space, right, and then 1, 0, and 1, 1, and so on, and we could do that, and arguably we're getting a little closer, right, to the actual phenomenon when we subdivide this way. And if you follow this out, let's split this again, and now it's 20. Split it again, then it's 40. We're always dealing with an average of 5 events across that many trials. So if we split this infinitely, this actually, if we follow this through mathematically, we're going to have the emergence of E. And what we're going to be able to see here is the emergence of E as a decay factor that is in relation to the arrangements of 5 events that can happen at any continuous moment in a fixed, let's say, span of time, right? And, if you want to kind of dig more into the emergence of E, I posted a couple videos. I don't know if anybody watched any of those, but I think E is really fascinating. Pi is really fascinating. It's nice to be able to just leverage some code and see how those emerge. And it's very accessible. It's not complex really at all. Or it's complex, but it's definitely within grasping almost immediately. The way that we see this is what we have manifest out of this, and this is actually derived from the binomial PMF. We end up with e to the negative lambda multiplied by lambda to the k over k factorial. And notice all we need here is a value of lambda, right? We need a value of lambda and a value of k, right? Where lambda is the expected number of events, the events on average for a certain span of time or volume, and k is the number of events for which we're looking for the probability. Okay, so in the binomial PMF, we needed some kind of probability. We set it at 0.5, by default. We've thrown that idea away here, and that idea is implicit in the lambda, right? Let's say we have 5 minutes and we have lambda of 5 events. Well, we're increasing the probability if we increase the number of events, right? So we can think about probability as being in relation to the count of events occurring. and we decrease the probability, as long as we hold 5 minutes constant. We decrease the probability if we decrease the number of events. If we say one event in 5 minutes, well, it's less probable. And I think that just makes sense. So I'll just rewrite this. The probability of lambda and k events occurring, the probability when you have a fixed lambda of k events occurring is going to be e to the negative lambda multiplied by lambda to the k over k factorial. So we can take this and we can start thinking about related phenomena. We'll also work out a problem in a second here. So let's think about some different Poisson-like things. The one that I like to use a lot is, let's say you have a camera in space and you're taking photos of the stars from different angles. And it's always going to be different. Let's say you're never going to get the same photo twice. And let's say you take 10,000 photos and you use that to construct the average number of stars that appear in each photo. Okay, so the average number of stars, let's just say, is 50, right? So on average you see 50 stars in a photo, and you have all these pictures, and there's a bunch of stars in these pictures. And this doesn't mean that you can't have 3 stars in a picture, right? It just means that's very unlikely. And we can now ask a question, well, what is the probability that, given that you see on average 50 stars in one of these photos, in one of these images, what is the probability, given a lambda of 50, given lambda is 50, that you see 45 stars? And we can just plug those numbers in. This is going to be e to the negative 50 multiplied by 50 to the 45, and that's going to be divided by 45 factorial. Okay. And what do we need to be able to qualify this phenomenon as being Poisson? Well, we're going to assume that these stars are not related to each other, right? We're going to assume that there's a consistent rate. Like we're not zooming in with any of these photos, right? We're keeping that constant as well, right? There are these things we need to qualify when we look at the phenomenon itself. A similar phenomenon would be, you have a square foot of yard, let's say, lawn, that is, and you've got all this grass on this lawn, and you say, well, on average, a square foot of lawn has, well, I don't know a number for this offhand, but let's say it's got like 1,000 blades of grass. Well, on average for a square foot of lawn, you have 1,000 blades of grass. Well, you can ask the question, what would be the probability of, selecting, if you select a random square foot of lawn, that you find 2,000 blades of grass or 1,050 blades of grass, right? We can ask this kind of question, and that becomes really powerful. So let's consider. Well, let me walk through a fairly simple problem. Well, it'll take a calculator anyway, so why don't we just use Python as a calculator? I'm going to have you code the Poisson Pmf really quick. This should be pretty straightforward. There are going to be 2 parameters, lambda and k. And I just want to point out before you code this, if I type lambda here, that's a keyword. So either use lam. I usually do lmbda, but Lambda itself is reserved. It's a kind of function. We have lambda functions. So just be careful of that when you write this. You can import you can import both e and factorial from the math function, or sorry, the math module, or you can hard code e and hard code factorial. Either way is fine. So let's do 4 minutes on this, and yeah, go for it. Okay, I'm going to code through this really quick. I'm just going to import e and factorial. So the way that you would do that is say from math import e comma factorial, and def Poisson Pmf. We're going to pass in lambda and k, And this is just going to be a simple one-liner, right? So we can return e to the negative lambda multiplied by lambda to the k divided by k factorial. And let's use this to answer an example question. So I've got one here, got a couple here. So on average, 10 people visit the ATM in an hour. What is the probability that 12 people visit the ATM in an hour? And we can think about constraints first when we look at these problems. One constraint would be, maybe this ATM doesn't have hours of operations that vary very much, right? So we're going to think about this as having some kind of smoothness in the day. If it's 2 a.m. or 2 p.m., it doesn't matter. There should still be a consistent rate of people visiting it. So let's answer this. The first thing we figure out is our lambda. So lambda, 10 people visit the ATM in an hour on average. And when you see that kind of on average, this happens in this amount of time, it's probably Poisson, and they're probably giving you the lambda right there. What is the probability that 12 people visit the ATM in an hour? Well, that's going to be our k, a k of 12. And when we call this, we can simply call Poisson of lambda and k, since I've defined those there. And that says code. And it looks like that's about 9.5% chance, a 0.0947 probability that 12 people will visit the ATM in an hour. And that may have a feeling of being lower than you might expect. 12 is not that far away from 10. But consider that we are thinking about the exact number 12, right? The exact count of 12 people. And, think about it as, 11 is closer than 12, right? And 10 is our expectation. So we already need to allocate those probabilities in terms of summing to 1, right? And so some of these probabilities may look a little lower than you might expect, is kind of the short story of that. I'll do one more of these. I'm going to paste this in to the Slack first, just in case anyone still needs it. And let's look at one more example. So this kind of harkens to the example I used of a telescope and stars. And I think with these kinds of problems, it's nice to find an archetypal problem, right? Like coin flips is a really helpful one for binomial, right? And I think taxis visiting a spot in Manhattan is really helpful for Poisson. Or I really like this one as an archetypal one because it kind of we can see that it's not just in terms of time. It can be in terms of area or volume. It can be in terms of a lot of different things. And Poisson has a lot of flexibility that way. And we don't want to just pigeonhole it to time. But in this one, a specific space telescope takes random images of deep space. On average, 23 supergiant stars are seen in an image. What is the probability that 2 randomly selected images will have a total count of 35 giant stars in them? So notice something that's happening here. Our lambda is not in relation to a single image, okay? 23 supergiant stars are seen in an image, and we're talking about 2 images, right? So we're going to change our lambda. So our lambda, the lambda that we're given is in relation to one image, but we're going to consider two images. So lambda of 23 times 2 is how we can solve that, or how we can think about that. And then our k is going to be, well, total count of 35 supergiants. Our k is 35. That's what we're looking for the probability on. So let's run that and find out. So it looks like that's about 1.6%, 0.016 probability. Now, we can ask other questions here, right? We can ask, well, what is the probability that there's 35 or more stars, right? Supergiants. Red supergiants, is that what it was? Supergiants. Let's just say supergiants. What if we're asking the question 35 or greater, or 35 or less supergiant stars in an image? Well, that might occur to you that that's a CDF, right? That's just a cumulative density function, and we can iterate over the counts from 0 up to 35 if we're talking 35 or less. So let's really quick. Well, you know, I already sort of talked about where Poisson's relationship to binomial. I think we can skip that. There's a little bit more derivation on these slides, but I think the takeaway is that we are increasing the number of trials to infinity, right? And holding the number, you know, the expected number of successes constant, right? And that has the emergence of E. So, oh, but you know what? This is cool, and I kind of want to share this code because it's exploratory. I forgot that I wrote these this specific thing into these slides, and because we have a little bit of flexibility on this, I'd just like to show you, you know, some kind of verification of what I'm saying, that Poisson is coming out of binomial, or we can see it that way. So we imported E and we imported factorial, and I'm going to go ahead and write combinations, the binomial Pmf and the Poisson Pmf we have written above, right? So I'm just going to write combinations and binomial Pmf. So combinations, right? This is easy. It's just n choose k, and we return, and I like to cast this to an int, the factorial of n divided by the factorial of n minus k, and that multiplied by the factorial of k. So that's our denominator. There's our combinations. And the binomial Pmf, I could just copy from binomial if I want. And it's right there. I could actually just import it from that other document, which would, just to show that. I don't know if you all have done that sort of thing yet. Well, why don't I do that? Let's say from binomial, let's import binomial Pmf and combinations. So I'm just pulling these in from the other file. So if I call binomial Pmf and let's say 10 trials, 5 successes with a probability, oh no, is this that weird binomial Pmf that I wrote? NPK, yeah, okay, well, that's fine. We'll just do 0.5 and k of 5. So let's just make sure that that's working. So notice we're getting this code running down here. That kind of means that I shouldn't do this import for fairly complex reasons that I'll explain after class. There's something called an if main block that we don't teach in this course that maybe we should, and I might do that in the future. Okay, anyway, let's just snag combinations and the binomial PMF. Sorry for that aside. And we'll continue from here. All right. So we have combinations, we have the binomial PMF, and we have our Poisson Pmf. So what we can do, where we can start at least, is let's start with a lambda of 10. And let's start with a k of 10. And what I'm going to do here is say for n in range k, this is n being the number of trials, right? This is n trials in range from k, and let's do up to 10,000. If I print the binomial results, so this will be the binomial PMF of n, k, and p, and I, just for our purposes here, am going to switch this around. kp, yeah. And then p, we're going to set a little bit differently than we have in the past. So our probability here we can think of as being lambda over n, right? Like 5 successes out of n trials, right? 5 successes out of 10 trials. And this is going to change as we increase the number of trials, right? So what we can see is this probability is just going to get lower and lower and lower and lower as the number of trials increases. And I should put n trials here. But we're holding k constant, right? So we can do this. We can show, we can describe this process and turn it into code, right? How Poisson comes out of binomial, we can do this. And I'll round this to, let's round it to 7 places. So we're printing the binomial results, and we can show that next to the Poisson results. And this will be the Poisson Pmf. We don't pass in n trials, we just pass in lambda. So here's lambda, which is just lam, and k, and putting that to 7 places. So let's run this and see what happens. And I'm going to put, this is a nice troubleshooting trick if you ever feel like doing this. I'm just going to put an input call right here, and that's going to force me to hit return after every iteration. Lam, not lambda. Yeah, I'm trying to switch over to lam because I always use LMBDA, so I'm probably going to make that mistake more than once. Cool. Let's run this. So we can see as this goes, we're approaching this probability lambda 10, k of 10, that ends up at 0.125. And we can sort of fast forward here, and we're getting closer and closer. And I think it's just good to do this sort of thing. Don't just trust, don't trust the concept, especially when you can write code for that concept. And we're getting closer and closer, diminishing returns a little bit here as we approach it. But even in 10,000 trials of this, we're getting very close to the result of the Poisson distribution. And that might tell you a couple things, like there are ways we might be able to estimate the binomial probability from Poisson, and there are ways that we might be able to estimate a Poisson probability from binomial. I think that's a helpful thing to see as well, is that even though these are two different phenomena, fundamentally two different phenomena, like we can use them in such a way to approximate the other. And we can conceptualize one through the lens of the other. So if you want, I'll just throw this code snippet in here. I think that's all you need. Into the Slack if you want to play around with this. And you know, I think it's just good to be able to do this sort of thing. So I said this before, and I'll just repeat it. Euler's number here, in the way I think about it, shows kind of a rate of decay, and that rate of decay is correlated with the spreading out of successes over divisions of this time, this construct of time, right? As we further subdivide time, we're spreading out successes, and that represents something like a rate of decay as we approach infinity. So let's do a couple of these problems. You're going to use the Poisson Pmf for this, and I'll just give you a couple minutes on it. So cars passing by an intersection at a certain time of day or year for the duration of a fixed amount of time will likely follow a Poisson distribution. The question is, a given intersection will have, on average, 15 cars pass through in 10 minutes. What is the probability that 20 cars pass through in 15 minutes? So I'll put 3 minutes on our timer, and just notice that our given lambda has to be in relation to the span of time. If we're talking about 15 cars passing through in 10 minutes, how do you modify the lambda for 15 minutes? So think about that, and as you solve this. Do y'all want 2 more minutes on this? If you do, give me a thumbs up. Okay, so let's go ahead and solve this. The hard part about this problem is that conversion of lambda, right? So how do we convert lambda here? I'm just going to show you a boneheaded way to think about it, right? We start off with this idea of lambda being 15 cars in 10 minutes, and so lambda's 15 upon first glance. But if we're thinking about increasing from 10 minutes to 15 minutes, well, we can just multiply that 15 by 15 over 10. And, we don't have to think about that very hard. We can just do that. And I think that's 22.5, I believe. Is that right? I think somebody else put that lambda in. Yeah, it looks like that's 22.5. And then our k here is 20. And we can just call the Poisson Pmf, which I'll copy. And we can see what this result is. Okay. It looks like that's about probability of 0.0769. So 7.6% or 7.7% probability that we'll see 20 cars in 15 minutes. Okay, so recall that the CDF has the word cumulative in it that implies accumulate, and the Poisson CDF is kind of nice because it is just a simple accumulation over the Poisson Pmf, right, of lambda. And this is where we pass in lambda and let's say I starts at 0 and goes up to the value of k, including the value of k. So let me just do this. So the Poisson Pmf, right? This is our Pmf, where we pass in lambda, and we are going to calculate I here, right? So if I was to write all of this out, which I could do, I could put the whole of, do something like this. If we wanted to represent it this way, e to the negative lambda multiplied by lambda to the k over k factorial, except we don't want k in there, we want I, right? So we want all the values between 0 and I, right? That's our Poisson CDF. All that is the summation of all results of the Poisson Pmf from 0 up until k. So you're going to code that. I'll give you 5 minutes to code that. Maybe make a little space. All right, go ahead and code that, and let's see where you get. Okay, so I'm just gonna go ahead and code this. For anyone who's stuck, I'm just gonna show that this might be easier than you think it is. This is called Poisson CDF. And if you think about the CDFs that we've done before, well, we're going to give the parameters that say static, right? And, with binomial that was P and N. In this case, it's just lambda. And I'm going to try to do lam. And we're going up to some high value of k, which I like to call it k high. And all we're going to do here is create an accumulator that we can then say for k in range, and we'll go up to k high because it's going to be from 0 up to k high, but including k high, and then we can say CDF is going to be incremented by the Poisson Pmf, where we pass in lambda and k, and then we can return the CDF like that. And we can use this to answer CDF questions. So let me take one of these prior questions and just adapt it. I'll take this one. So the Space Telescope, on average, 23 supergiant stars are in an image. What is the probability that two randomly selected images will have a total count of 35 supergiant stars in them? A total count of 35 or fewer. How about that? So that subtle change, well, we can solve this. We can say print Poisson CDF, and we're going to give it a lambda of 2 times 23, right? And our k high is going to be 35. So up to and including 35. And notice that's a pretty small value, right? Now, what if we were thinking of up to and including 46? What if I change that? And we can see what that starts looking like. Now we're right around 50%, right? We're right around 0.5. And that makes sense because that's our expectation. We would expect, to encompass half of the distribution up to the expectation. This is a little higher than the expectation. We'll see why in just a moment when we pack these into a dictionary, which is the thing we always do, right? We pack the results of these things into dictionaries. I'm going to skip this next breakout and just answer it really quick to give an example, another example. Okay. Given intersection will have on average 15 cars pass through in 10 minutes. What is the probability that more than 15 cars will pass through in 15 minutes, right? So this looks similar to this problem up here, oh yeah, okay, never mind, I didn't paste the text in before, but yeah, the problem that we were looking at before, where we have to transform the lambda, right, where our lambda is, it's not 15, but it's 15 times 15 over 10, and here our k high, well, we have to, this is one of those places where we really do have to think about this in terms of being the complement, because it turns out that, let's say we have a Poisson distribution, right? And we're going to start at 0 because we can't have less than 0 events. The Poisson distribution might look something like this, where this goes out to infinity, right? And we can consider this isn't a real thing, but we could consider, the probability of infinity minus 1, right? If that's a number that we can say exists. Now, that's a massive number that has a near zero probability, but it's not zero. So we have the probability that, even though this would violate certain constraints of physics, we could say, well, there's a probability that there's 9 million cars that are going to pass through in 15 minutes. What is that probability? It's going to be really close to zero, but we have to consider that we can go all the way out to the right as far as we want. So we can't, in this case, just simply count the probability that of k is, 16 plus k is 17 plus k is 18 plus k is 19. We're going to have to stop somewhere just because of computation. But what we can do is we can take the complement here, and we can say that this is just going to be the Poisson CDF with our lambda. And then we're thinking about 15 or less cars, 15 or fewer cars, that is. And if we take the complement of that, right, if we think about this in terms of this distribution, we can, we don't really care about this value except in terms of the complement that we want to find, which is the probability of anything out that way. So we're just going to take the complement. And let's see what that is. So that's very probable, right? That we're going, it's 93.65% or 66%. That's very probable that we're going to see more than 15 cars pass through this intersection. Now, why is that? Well, it's because our expectation is around 22 and a half, right? And so if we think about that, we're including, if this is where, 22 and a half falls, right there, then we're including not only half, we're including a lot of, what's to the left of our expectation as well. Okay. So let's take a 6-minute break, and when we get back, we'll get into some dictionary manipulation. All right, I'll see y'all back here shortly. All right, so what we're going to do is, code that classic dictionary function that we've been coding, where we have as a key, the value of k, and as the value, the probability of k events occurring. That's going to look a lot like things that we've seen, right? The binomial PMF dictionary, for instance. So we're going to do that for the Poisson Pmf. And in this case, we're going to go from the low value of k to the high value of k, right? So we've got lambda, low k, and high k, and we should be inclusive of high k. So let's do 6 minutes on this. And yeah, if you have any questions, put them in the Slack. But that's the function that you are going to write. Okay, let me know if you want a couple more minutes on this. If you feel like you're almost there, give me a thumbs up in the Slack, and I'll put a couple more minutes there. Okay. All right, I'm adding. I'll add 2 minutes. Okay, I'm gonna go ahead and code this, and yeah, this is, again, like the kind of thing that we will often ask on a technical interview. So here we've got the Poisson Pmf dictionary, and we're passing in Lambda, a low value of k, and the high value of k that we want to include. And basic pattern here is you create a dictionary and we collect into that dictionary. In this case, we'll say for k in range, and we'll go from low k to high k plus 1 because we want to include it. And I can just say, I don't need to check membership or anything here. We're not modifying these values after we set them. I can just say d sub k gets Poisson Pmf, and we pass in lambda and k. With that, we can return the dictionary. And I'll just call out to this. And let's set a lambda of 10, low k of 0, and a high k of 30. And I can just say for key and value in d.items, let's print that key, and let's round the value to 6 places. And I think that looks good. Okay. When we run this, not timer. When we run this, we're going to get, this whole range of values. Since this Poisson is built around 10, we could look at potentially just between 5 and 17. And something I want to point out here that is just kind of cool. The probability of 9 events and 10 events is the same, right? Like, look at these probabilities. And if we put in, well, let's put in a different value. let's do a lambda of 4, and we'll go up to 10. And just see. There we go. Notice, so our lambda is 4. The probability of 3 or 4 is the same. If you do the math, if you just sit down and work this out by hand, you'll see, oh, well, okay. That's. I think this is a strange facet, interesting facet of Poisson, and I have a hard time explaining it to myself, and I kind of want to take a little time at some point and actually explain that to myself. Well, why is that? Why is the probability, if our lambda is 10, why is the probability of 10 the same as the probability of 9, right? Why are those the same thing? If you come across that information before I do, let me know. I just think it's kind of a cool thing. All right, so I'm looking at this next breakout, and yeah, I think this is good. So this is not necessarily a coding breakout, but I want you to think about this in light of this Poisson Pmf dictionary. So we're observing a phenomenon that for some reason we know that it perfectly follows a Poisson process. Given a certain number of observations, let's say 10,000, how would you determine how many events to expect for each value of k given lambda of 10, low k of 0, and high k of 30? So think about this. I'm going to put 2 minutes on here, and put your thoughts about how you would estimate the counts of observations for certain values of k, given this prompt, and put that in the Slack. I am really sorry. My microphone was off. Well, let me start saying all that again. Okay, so let's think about an actual phenomenon here. And let's go back to this idea of images of stars and approach this question that way. And I just want to say that this is actually much simpler than you might be thinking. It might even be painfully simple once we look at it. So let's say we take 10,000 zoomed in photos of the night sky on some clear night. And we know, we have some prior understanding of the expectation for the number of stars in what we would expect to see, the average number of stars in our photos. In fact, we could even potentially take the average of stars across these photos. And let's say on average we see 20 stars per photo, right? There's our lambda. How many photos do you think would have 0 stars in it? How many photos would you expect to see that have 1 star, or 2, or 20, or 30, right? Now, this may not be immediately obvious, because we framed it as some kind of question. But I just want to show you how simple this actually is to think about. We can just take this function, or this traversal of the results of that function, right? And we can multiply this value by 10,000, right? And this is going to give us expectations for each k. So, let's actually multiply v by 10,000 so that we're not getting these kinds of numbers. So looking at this, let's take this out to high k of 30, for instance, and let's set lambda to 10. Let's actually take high k out to 50, just to be that person. And I'm going to round this to, I'm just going to round it. I'm going to round it to an even number, because we're not going to assume fractional photos, right? Okay, so what we start seeing here is, well, we don't actually expect to see any photos that have no stars in it through this idea. We might see 5 photos that have 1 star, and if our lambda, our lambda is 20, isn't it? Let me run that again. Okay. So here, we don't expect to see any photos that have less than 5 stars, and we only expect to see 1 photo that has 5 stars in it. And when we get up here, well, there's going to be 888 photos that have 20 stars. If this truly follows some kind of Poisson distribution, this is what we would expect to see. Now, is that what we are going to see? No, not necessarily, right? Because this is a sample. And what we would likely do is do this every night for, some number of nights, and then we would average those results, but these would be the counts of photos that we would expect to see. And we just figured that out by multiplying the probability by, to get the counts, we just multiplied the probability by the number of samples that we're considering, which in this case is 10,000. So just 10,000 by the probability gives us an answer to that question. And yeah, let's call it there for Poisson. You have the code base in the slides and obviously in this file. Poisson is one of the distributions we really expect you to know for the technical interview. Along with the binomial distribution, we do really expect you to know those. You don't need to know as well the geometric distribution, but we're going to cover it. We're going to cover some of it, and I'll leave the rest of it for you to complete in the Learn materials. In the future, we might have, we might cover it in more depth in the technical interview. We may require it a little bit more, but binomial and Poisson are really the ones that we want you to understand. We can think about the geometric distribution as being built on the binomial process much more directly than the Poisson distribution is, right? We kind of had to heavily transform the Poisson distribution we had to heavily transform the binomial distribution in order to take it to the Poisson distribution, right? We had to increase the number of trials to infinity. What the geometric distribution does is actually really simple when you break it down. Let's say we have a coin flip, and it's just a standard coin flip, probability of 0.5. We might ask a question, well, what is the probability, right? What is the probability of getting heads on the fifth flip? And we can start counting this pretty easily. And maybe instead of fifth flip, I'll say third flip, just to be able to do this by hand. We can solve this in a counting approach, right, if we really want to. And the simplicity of this we'll see reflected in the probability mass function and the CDF. So this is 0, 0, 0, right? Tails, 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 heads. And then, right, that's our target. That's the only one that we actually, in some way, that's the only one that we actually care about. That's the only version of success that we see here. And but if we count this out, right, 0, 0, or 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, we're starting to look at, what is the probability of getting this, getting a heads on the third flip. And so you can see that this question is actually pretty easy to consider. But let's approach it from the point of view of the PMF itself. The PMF here can be a little confusing, and that's because we actually have two PMFs. And what I'm going to say and what we're going to do, we're going to choose one PMF, okay? And we're just going to use that one. Usually, in past classes, I've taught both of these and had people code them out as kind of a coding challenge, like how do you use one over the other, but let's not do that today. Let's just consider calculating the number of trials up to and including the first success. So this is going to be our PMF. Look at the simple construction of this, and also look at the recurrence of that, right? Like that's just taken straight out of the binomial PMF. Of course we're seeing that here, but we'll actually see that construct in all kinds of statistical concepts. So this is going to be our PMF. We're going to think of, well, let's ask that same question. What is the probability of heads on the third trial? Well, the way that we think about that is the probability that x is equal to 3, right? Up to and including the first success. Success happens on the third coin flip, right? So this is just going to be 0.5 multiplied by 1 minus 0.5, which is 0.5, and that's going to be k minus 1. Our k here is 3, right? Should call that k. So that's going to be k minus 3, 3 minus 1, which is 2. So this is going to be 0.25 times 0.5. And something that may stand out to you with this is that if we are considering a probability of 0.5, Well, the probability of getting success on the first trial is 0.5, right? The probability of getting that first success, the first success on the second trial, is going to be 0.25. The probability of getting success on the third trial is going to be 0.125. And then, so if we think about this like this is 0.5 to the first power, 0.5 to the second power, 0.5 to the third power, and then if we continue on with this, 0.5 to the fourth power, 0.5 to the fifth power, and so on. That's with this probability fixed at 0.5. But this is going to hold, right, for other probabilities. And I think this is a very simple series to get. We actually call this the geometric series, right? If we apply this 0.5, 0.2, 0.25, 0.125, if we apply this series as coefficients on some variable, then we might be applying something we would call geometric decay, all right? But this is a simple geometric series, and we can see how it's constructed both in terms of exponentiation, but we can break that down in terms of the PMF itself. There are some nice aspects of the geometric distribution, right? Where, well, we only want one of these. Sorry, let me grab this. The mean, or expectation up to including the first success, the expected number of trials here is just 1 over the probability. That's kind of cool. Very simple approach here. And then the variance up to and including the first success is 1 minus the probability over the square of the probability. So that's this is just it's just a very kind of friendly distribution, you could say. A little bit friendlier in some ways than even the binomial distribution. But underneath this is a binomial process, and we can see that very clearly. So I'm going to have you code the geometric PMF, and we'll use that to answer a couple of questions. And it's asking here for an inclusive equals true parameter. I'm not going to have you code that. Let's just ignore that. So all you need is the probability and the inclusive and k as being inclusive of the first success. So we're asking the question, well, what is the probability of success on the third trial? Well, in that case, k would equal 3. Okay. So let's take 4 minutes. Well, let's take 3 minutes on that, right? Because it's just this simple function right here. Okay, so I'm just going to code this really quick, and then we'll look at this through the lens of a couple problems. So pretty straightforward, Geometric Pmf, and we're going to pass in the probability, the value of k, and we're going to we skipped that inclusive flag. So this is just a return of the probability minus the complement of the probability, where the complement of the probability is raised to the k minus 1. So let's think about answers that we can get, right? We're flipping a fair coin. What is the probability that we get the first heads on the 7th flip? Well, that's k is 7, and probability is 0.5, and we can see pretty quickly that this is the geometric Pmf of 0.5 with a k of 7. And notice this is tiny. This is we have a 0.78 percent probability, right, that we get this on the 7th trial. Now, if we are considering getting this on the first trial, right? This is heads on the first trial. That's just 0.5, and we can see, if we change this to 2, 0.25, and in fact, we can just say for k in range, and since we're including the success, we have to start at 1. We can go from 1 up until 20 and just see what this looks like. And we can see very clearly the geometric decay here for 0.5. So here's a better, well, I don't want to say a better question, but here's a question that I think is indicative of the types of phenomenon we might be considering. Okay, so let me just grab this. You have a series of routers transmitting packets of data. There's a 0.99 probability that a given packet of data passes through the router. What is the probability that a given packet is lost in the 15th router? Okay, so when we're thinking about this, if we're, we can draw a picture of this. There's this packet, right? This is just some digital packet, and this is going to go through a router, and that's going to go through another router, right? Then through another router, and so on. And the idea is that this has some destination somewhere. We don't know how many routers it's going to go through, but we're assuming, for this question, we're assuming that it's more than 15. And so, we're seeing that there is a 0.99 probability or 99% chance that we're going to get success. So, our assumption is that this is going to do pretty well. And the question is going to be, what is the probability that this packet of data is lost in the 15th router? So go ahead and solve that, and I'll just put 2 minutes here. And just think of this. This is the type of phenomenon where you might apply geometric. So this is an interesting problem in some ways because, well, there's a 99% probability that a given packet of data passes through the router. But we're thinking about this in terms of the loss of that packet, right? And so this brings up the question, well, how do we consider the probability of success? Probability here is actually going to be 0.01. And so, or we can approach this, and I think it's easier to approach this as the probability of losing the packet. So, so let's think about it that way. And I'll just close that. So we're talking about, I'll just paste this in again so I have it. The probability that a given packet of data is lost in the 15th router, well, that's going to be our k, right? K is 15. And let's consider 99% probability that a given packet of data passes through, but we're thinking about this in terms of being lost. So the probability of it being lost is 0.01. And then we can just call the geometric Pmf for P comma K, right? And let's see what we get out of that. Now that is tiny, right? That is really tiny. So, you know, of course, you can solve this as well via the complement. That's fine. But I would go ahead and say probability of it being lost as being the way to do this. It'll be less confusing. If we modify this question just a little bit, right? What is the probability that a given packet of data is lost on or, in or before the 15th router? We can approach this as a simple accumulator, and that would be fine. We could write, def geometric CDF, and we have the probability and ki here, right? And we could make an accumulator and go from k in range 0 to k high plus 1. We can get the geometric Pmf of P and K. And we can return that accumulator. So if we want to answer that question, we can pass these values in again on the geometric CDF. And we should see a good, there's a pretty good chance, or there's an increasing, how do I say this? Let's run this. Oh, what am I doing wrong here? That's what I'm doing wrong. So our chances have increased. Now, why might we ask this kind of question? Well, if we're seeing packet loss at some fairly high rate, and maybe we don't know where it's happening, but we're not seeing that packet hit the 16th router. We don't know if it's happening in the 15th or the 13th or the 9th or something. We might start, focusing in and saying, well, are we seeing packet loss at greater than a rate of 15% for passing through these 15 routers? Are we? Because if we are, then it's likely that we have some faulty hardware somewhere, or we have some other software issue that's happening in a given router. And then we can go router by router, and we can ask the question, well, what is the probability that we would lose a packet in the 15th router? And what is the rate at which we're observing that? Is that rate greater than what it should be according to this theoretical distribution? A cool thing about geometric, and I'm just going to point this out before we wrap up, is that we don't need to use an accumulator pattern here. We actually have a closed CDF. And that closed CDF is very simple as well, right? And it's right there. So the probability that x is less than or equal to k is just 1 minus 1 minus p to the k, which is kind of brilliant. It'd be nice if everything had that level of, you know, that ease of formulation. But so we can just return here 1 minus p to the k. So I'll go ahead and paste this in. I don't think you need any of that. We have the Geometric Pmf. You just need the geometric CDFs. Okay. That's class for today. I think Monday is going to be a pen and paper day. Let me just double check that. Oh, actually, Monday is a day with Clark. And then, okay, and then we're going to cover the normal distribution and the exponential distribution and a continuous uniform distribution on Tuesday, and then Wednesday is actually the pen and paper day. So scratch that. You're going to be meeting with Clark on Monday and coding more functions, a lot more function practice. So yeah. Thanks so much, and I'll stay on for questions. Feel free to come off mute at any point.